right. Hello, everybody. We're right on time. Welcome to the nice number 148 talk. Today, we're going to discuss some very interesting topic around knowledge distillation and information distillation. So we know this is a very important topic for long decades, and especially for the larger model that comes out recently, it brings some new opportunities and challenges for this same topic. So recently, people tries to distill those strong capabilities from the large models to small models. But what if we do not know the chain of thought reasoning process of those large models? So today's talk, we're going to try to discuss this problem and how to solve it. So today, we're honored to have our speaker, Emiliano. Emiliano is a friend of me at Mila, and we actually know for a long while, and we previously did lots of projects on personalization and recommender system. And recently, Emiliano is focusing mainly on LLM agents, especially in complex multi-step environments by leveraging their conversational properties at the user level. And also, he's a visiting researcher at ServiceNow at Montreal, also working on large model reasoning for agentic tasks. And I'm today's host, Haolun. So without further ado, Emiliano, it's all your floor. You can share your screen. Thanks.
Perfect. Thanks, Haolun. Let's get started. Thanks everybody for coming today. And then everybody in the recording, thanks for watching. Today I'm here to present to you guys my recent work on privileged information distillation. This was a joint work with some amazing collaborators, both from Mila and ServiceNow. And like Haolun mentioned, my name is Emiliano, and I'm a third-year PhD student at Mila. Okay, so with that, let's get started. So let's first discuss a little bit as to what the problem that we're trying to solve is. As Haolun mentioned, one of the main things that we're going to try to solve is the problem when a large language model, we're trying to distill from a larger model, but we do not have access to their chain of thoughts. Now, this model is actually a little bit of a category of models in which we're trying to solve, and those are the types of problems in which we want to distill from something. So we want to add capabilities onto a model. So here I have kind of like a diagram of a situation that's very common in RL training, specifically when doing it with LLM. Here on our x-axis, we have some sort of reward over trajectories and our prompt. And then over this dashed line, it's positive reward, which means it's good. And then over this, behind this dashed line, it's negative reward, which means it's bad. Now, for most tasks in RL, specifically with LLM, the distribution, so these are the output distributions. So when you actually sample tokens and you score the reward on whether the model did a good job or a bad job, most of the distributions look something like this, where you have some support over correct trajectories, also over correct outputs, and you have some support over negative or incorrect outputs. And what we want to do is we want to bring this mode down. So we want to shift the mass from this region down, and we want to bring the mass from this region up. And there's a few different works, such as the ones I have like listed down here, that kind of advocate that a lot of reasoning in LLMs due to different facets, could be something like data contamination and things like that. Specifically, these issues appear at an academic scale, are trying to sharpen the modes that exhibit correctness rather than trying to shift the mass of the distribution onto some higher reward regions, for example. So basically, to summarize, in RL for LLMs, we're not really discovering new modes or trying to expand our capabilities somewhere over here, where my mouse is pointing, but we're just trying to bring this mode down and push some existing mode up. And this is kind of how RL and LLMs is kind of understood currently. So this is a big problem, specifically because for a lot of tasks, our models don't really have trajectories or like any trajectories in their support, right? So we can think about tasks specifically when we were working on this. I think models have gotten better, specifically at the frontier at this now, but when we were working on this, there's a lot of models struggled with complex multi-turn agentic tasks, such as like tool calling environments and things like that. And in this scenario, something that you see very often is that your model distribution looks something like this. where you have no support over correct trajectories, and then you're trying to chase some target policy here, which is this green one, right? And without having any like mass on the positive region, it's basically impossible for you to bootstrap yourself out of this situation. Your model only samples like negative traces, and getting yourself to kind of like get yourself here is basically unfeasible. So if the model can't learn, and if the model if the model can't bootstrap itself via RL and learn, then there's really nothing that we can do with just via traditional RL techniques. So obviously this is not necessarily a problem, and there's ways to solve it. So the most common options to this is to either just kind of like pray to the RL gods that we're going to get some trace magically here through possibly some like smart curriculum or like reward engineering that we're going to finally be able to sample from this region. But this is still unpredictable and possibly unlikely. The more common approach, which is very thoroughly used by most, I would say most labs, is that of distilling / supervised fine tuning from a bigger model. And in this case, what this will do is basically it would expand your support. And we'll go a little bit more into detail as to what we would do here, but it would expand your support in a way where you're going to have some mass over this region, and then you can bootstrap yourself via RL, for example. The final option, which is very similar to distilling and SFT, is more mid-training, where you kind of like cater your pre-training data to look a little bit more like the task that you're trying to do towards the end of it. And that way you have a little bit more support or probably mass here. But these are all these things are kind of just like tricks to be able to do this. And something that we do in this work is we kind of like think out a little bit outside this box. Still within like the framing of distillation, but like thinking a little bit outside the box of if there's any other way that you can kind of fix this problem. So yes, interestingly there is, and the way that you go about fixing this problem is through a very unique and interesting, and I would say economically shifting capability of these models, which is that unlike any other models, language models can understand language. So you can type to them and they will have a sense of understanding as to what you mean by it, right? So the main thing is, what if we can just condition our policy on some set of like what we call privileged information? And I'll go into what this means into a second, but like what if we can add another conditioning factor to the same policy? So these two are the same model, and now our distribution gets shifted like this. And now this looks like something that either can learn via RL, or like maybe we can use sample from to teach this model. So there's like a bunch of possibilities that we can do with this. So there's like this interesting setup where we can maybe get ourselves out of this bad situation. So now to make it concrete, this privileged information is something that may not be available at test time. So in a lot of situations, privileged information is available at test time in the form of like RAG, documents, and all these things. But for the sake of this talk, we're going to assume that privileged information is something that's very specific to the task we're trying to solve. And while it may be available at test time, it may not be relevant for the tasks that we're trying to solve, for every task that we're trying to solve. So you can think about this as like a solution to a math problem. You may still have the solution available at test time, but it's not going to be relevant to every single problem that you encounter. It's only relevant to the specific problem that you're trying to solve, right? So these are kind of the things that we mean by privileged information. Okay, so now let's be a little bit more specific, and let's kind of like illustrate what we mean. So to kind of convince you that this is useful, like take for instance an LLM that produces an answer here. It's not hard to believe, and there's plenty of examples that if you condition this LLM on any sort of like additional information, such as successful trajectories, retrieval augmented generation, multi-agent pipelines, or like hints, these LLMs perform substantially better than when they're not conditioned on such information, right? So this is kind of like an illustration of what we mean, right? Where these two LLMs are basically the same model, even though they're parameterized here differently. That is simply just to indicate that they technically don't need to be trained the same, but initially they're the same model. So if this is a Quen4B, this is also Quen4B. And basically, once we condition on any of these privileged information, now our distribution shifts to this, right? Okay. So now quickly describe the setting that we actually like ground our work on, and also give like concrete illustrations as to how some of our privileged information looks like. So we base our tasks on multi-turn agentic tool use benchmarks. So we specifically use Tailbench and Travel Planner. Tailbench is a multi-turn conversational benchmark in which you're basically trying to accomplish tasks for users. So here, for example, the user comes to the agent and asks us to change the flight. Then the user has access to tools such as get a reservation, cancel the reservation, all these different things that is able to do through the tools to be able to kind of accomplish tasks. Likewise, on Travel Planner, it's a very similar setup, but the main difference is that here the user is coming to the agent to help it plan a trip, and then the agent has to maneuver a set of tools to be able to come up with a feasible plan for the agent, where the user has certain constraints that must be met and the agent must have them. So just to reinforce, these are multi-turn agentic tool use tasks that are significantly more complex than a lot of things that other RL papers are trying to benchmark. So yeah. Okay. So again, now let's go a little bit further and try to ground this in how specifically we do this. So we focus on distilling closed source frontier models. So frontier models, for example, Opus, Gemini, and GPT-5 do not release their reasoning traces. So if you were to try on typically a typical pipeline where you're trying to distill some larger model, specifically with a reasoning model, is you require the reasoning traces. So basically, when any of these models do not actually give the reasoning traces, this breaks this pipeline because we still receive the action that the agent took in the environment, but we don't know why they did that action. Sometimes you get a compressed summary that acts as an explanation, but this is not the true chain of thought. So instilling on this can still degrade performance. So the chain of thought is actually very, very important. And this is kind of one of the main things that makes these models significantly better is the reasoning process, right? So not being able to copy or learn from it degrades distillation significantly. So just basically this leaves the setting that we have below, where we have access to a prompt or an instruction and we have an action or a tool call. And in our work, we specifically collect traces from DeepSeek B1 trajectories. And I'll get into this for a second. But the reason we chose DeepSeek as a frontier model to distill from is because DeepSeek actually, unlike these other proprietary models, actually does output the chain of thought reasoning. And this is important for us to have as an academic study because we want to explore how the model would have performed if it had access to this information and how it performs when it loses it, right? So basically when we evaluate models that are trained on the full chain of thought reasoning, this could act as kind of a soft upper bound of how good you can get if you have access to the full information, right? So this is the main reason why we didn't do it from any of these models, apart from legal reasons. But also DeepSeek B1 at the time we did was a really, really good model and competing with Opus, Gemini, and GPT. I believe it was not even GPT-5, but GPT-4 at the time. So yeah. So again, just to reemphasize, these models do not have their chain of thought reasoning, which is very important for distillation. So the main problem we're trying to solve is how can we distill from a frontier model without reasoning traces. So basically, we're trying to find a way to obtain this chain of thought Z, right? Okay. So now that hopefully that's more or less clear, we're going to go into how we generate the privileged information. So since we assume that we have access to the prompt and the tool calls that were made by DeepSeek, we can turn these into privileged information. So there's different ways to kind of represent them as privileged information. So for example, here, we can just take the raw tool calls and arguments that DeepSeek actually output in the environment. So this would be something like ID by email, and then you have the full email as a function parameter. You could also have something that's get order ID with the full parameter for the ID. And moreover, you can also have a completely different type of privileged information. So here, this could be just tool calls. So we drop the arguments. So here, rather than passing ID by email, we would pass ID by email just without any argument. Same thing with get order. right? And then finally, the other type of probabilistic information that we test is this one for self-generated hints. So we ask the same model that we're going to fine-tune to take DeepSeek's actions and summarize them into a hint. Now, what this does is, as a whole, this kind of gives us 3 different types of privileged information, all with different like granularity of the information they hold. And this is important because, as we will see later in this work, different types of privileged information make the model behave differently and change the training dynamics. And different types of privileged information will shape the distribution that we get, basically, from these prior slides. Different types of privileged information will shape this distribution to look different, and it will affect the dynamics as to how we're able to finally learn a student that must act without this privileged information. So that's when it's important that we test basically 3 different kinds. And again, I'll go into a little later in the presentation, I'll go into a little bit of more specifically like the properties and how they differ. And these are more like mathematical properties, like for example, like the Kale divergence or the utility that these privileged information give you and how they vary. Okay, so more concretely, like implementation wise, how this looks, this literally just looks as we're just adding this to the string. So we're just feeding this to the model and we're adding some like hint tags and we're just feeding these into the prompt. So this is actually like a very simple procedure. There's like nothing that you really need to do or change in the architecture. And it's a very special property of language models where you can just shape their output distribution by adding this information into the prompt, right? So this procedure is very simple. Okay, so now that we have this kind of idea of like these different types of privileged information and we kind of have the goal of what we want to do, let's dive a little bit more into like, what is the problem that we are even trying to solve, and what are some of the techniques that you can do from this? Like from first principle, what is the problem that we're trying to solve? Okay, so in the setting, to be specific, we assume we have no complete access to a frontier model. So we assume that we have access to their actions or some sort of like latent actions that we obtain somehow. These, by the way, these actions could be human actions, for example. And there are tasks that the model itself cannot solve, so it has no support over. So basically, we're in this setting where we have no support over successful outputs and we have no successful traces and no larger model. So what can we do? There are various ways to like do this, but basically these boil down to forward versus reverse scale optimization. And for those that are unfamiliar, I'll try to go a little bit more in detail as to what these mean. And the other thing is, do we need to train some sort of teacher or do we not? So here the teacher refers to the model that is conditioned on the privileged information. Okay, so to make things a little bit more concrete, we're going back to this picture where here the purple curve is the model conditioned on the privileged information. So here you can see the conditioning factor, and we call this the teacher. And here this curve that's moving is the model that's not conditioning with privileged information that we're trying to that we will ultimately deploy, that we're trying to train. And this is a typical distillation pipeline where you have a teacher and a student. And the only difference between these two is they're the same model, just that the teacher is conditioned on privileged information. So essentially here, what we have is we have a teacher that's already pretty good. So if we do forward Kale, which is equivalent to supervised fine-tuning, so what that means is we take samples from the teacher and then we do supervised fine-tuning, so just typical binary, typical cross entropy on the target text that the teacher produced with the student, and then we kind of like learn it. This is what happens, which is that basically the student is able to cover the modes of the teacher, and this is a very specific, well-known property of forward Kale. And one of the negatives of forward Kale, although it's very useful in practice, is that you are just trying to cover the modes of whatever distribution you're targeting, and you can end up in a situation, as we do here, where your biggest mode actually ends up being in a very low probability region for the distribution you're trying to target. And this is a byproduct of you just trying to spread your mass as much as possible. So yeah, and then another final important like distinction here is that, as you can see here, one of the main reasons why I keep saying that these two are the same models, and you can think about the same models, but they have different parameters here. The reason for that is because technically here the teacher stays frozen and the student is moving. So because the student is moving, that technically the parameters between the teacher and the student are not the same because the teacher is still the initial checkpoint, but here the teacher is moved. Okay. So with this out of the way, this is kind of the setup that we're going to be working with, and this is kind of your most typical thing that you can do, the easiest, the least labor intensive. But as we just saw, it's a little bit suboptimal. So what else can we do? So there's a lot of works recently that kind of started like coming up with this idea. And if anybody of you have seen this self-distillation work, this is kind of like what they're doing. So self-distillation basically boils down to this idea of reverse KO. So rather than doing this forward KO where you're sampling from the teacher and then fitting the student, you literally just switch the order of the of which one is on top and which one's on the bottom and which one you're sampling from. And now you're sampling from the student, where you're still trying to fit a mode, or you're still trying to constrain yourself to the distribution of the teacher. And what this means is that now, rather than being mode covering, what you want to do is seek a mode. So you're trying to collapse all your probability into a mode of the teacher. And this will basically help you like find some sort of like local optimum. Now, importantly, this sort of reverse KO procedure does not really tell you which mode to go to or which region to go to. You're just going to try to find the easiest to fit mode. So as you can see here, there's two modes, well, each of which we could fit. But because there is basically one mode that is closer to our initial starting point, we're just going to fit that because there's nothing specifying that we should be fitting either all the modes or a higher reward mode, right? And again, this is one of the things that most of these self-distillation works, this is how they operate. So if there's this problem where we're fitting a lower reward mode, what is a very simple fix that we can do? And that is we can literally just add the reward term. So adding this reward term should alleviate this. So now we're not only are we incentivizing the model to learn from higher reward modes, but we're also to seek a mode that has high reward and act like under high distribution as the teacher would, but we're also telling it to find the higher reward mode. So this is kind of like why this two bimodal distribution comes into play, where now rather than just fitting the lower reward mode that's easier to fit, we're going to try to force the model to fit an even higher reward mode. And this can all be balanced. This kind of like trade-off between the reward and the KL can be balanced via this like parameter beta. But this objective has two terms. One simply just tells you to find a higher reward region, and the other one tells you to find a mode for the teacher. And when you put these together, it's telling you to find a higher reward mode for the teacher. So basically, this is what we're doing. Okay. So in all of these scenarios, we've kind of like assumed that when we condition on privileged information, our teacher looks very good or fairly good, right? So if we look at any of these before, the teacher has two modes that are already like higher, like over the zero line. So they have like moderately high reward. But what happens when you have a distribution that looks something like this, where actually now our teacher is below the zero reward, right? So if we try to do like the initial self-distillation or even like for the KL setup with SFT, with SFT, we would end something like here, which most of the mass would still be negative. And with self-distillation, we would like sample from this peak, which would not be ideal, right? So in this situation, we kind of end up in a bad stage because we don't have a great teacher to distill from. So the most intuitive thing to do is, because we have access to this model and we can train it, is what if we just train the teacher? So how we train the teacher is with a specific loss. So there's like a variational derivation to come up with this from variational inference. But in short form, what this loss is doing is this is just saying, let's make the teacher better by training the teacher on policy. So we're sampling from the teacher and we're trying to teach it to become better. And also make learning from the teacher easier, because the teacher is ultimately what the student is going to learn from. We want to have this term that says the teacher should stay moderately close to the student, such that when the student is trying to learn from the teacher, its traces are not too off policy. And this just means that the teachers look like something that the student would produce themselves, so it's easier for them to learn from. And what this is called is this can be thought of as like a variational EM algorithm, which I won't get into much of the weeds of this, but basically this boils down into a two-step procedure in which you first train the teacher, to kind of like fit a mold of like your target distribution like we did here. And then you train the student onto the teacher using the supervised fine tuning. Now you could use you could use the supervised fine tuning. You could use the reverse KL setup as well. Here, supervised fine tuning is just the one that's like is typically used with variational EM, so that's what we used. But as you can see here, this process has like two stages, right? Like first you train the teacher, then you train the student, and then not only that, the teacher has different weights than the student, so it's like a complicated process where you have to navigate all these different like things. So what we do is we introduce PyDistill, which is an algorithm that allows you to circumvent the negatives of the prior algorithm I presented, and basically just do everything in one shot. So we propose this objective that where you can jointly train the teacher and the student, and you can balance them with this hyperparameter alpha. So the student loss is exactly the same thing as the teacher loss. The only difference is that we sample from the teacher, and we use this important sampling coefficient to train the student instead of the teacher. So this, when you backpropagate through this objective, you'll be training the student. You won't be training the teacher, basically. And then this value of alpha will modulate how much you want to train the teacher versus how much you want to train the student at any given stage. And rather than becoming this like two-stage algorithm where you first like train the teacher and then you train the student, you do everything in one shot, which is significantly more efficient, convenient. And since it's one model, since these models are now sharing weights as well, so these models are complete equivalent copies of each other, you only ever need to have one model in memory. So this is also very memory efficient. So there's a lot of upsides of doing it this way or the other way. So in practice, this gives you different configurations, and we're going to explore different values of alpha. So we're going to explore alpha in 0, and this means we only train the student. So we zero out the teacher loss, and we're only going to train the student. And then we're going to do alpha of 1, and this means just training the teacher. So we cancel out the student loss, and we're only going to train the teacher. And then we're also going to do joint training, where we train the teacher first, and then where we train the teacher and the student at the same time. Okay, now to visualize how these kind of look, and this is kind of best case scenario for all these algorithms. These are basically best case scenarios. So we're not saying that this happens in like every single case, but these are kind of like in the optimal case, how do these look? So in this scenario, basically when we're doing student-only training, so alpha equals 0, what we would expect to see is that the student is trying to tail behind the teacher. But something we observe in practice is that when you allow the teacher and the student to share weights, even if you're not training the teacher implicitly, the teacher gets better. So the teacher actually like gets pushed along by the student coming towards it, and this teacher is able to improve. And it was quite surprising because we didn't really expect the teacher. We actually expected the teacher to get worse, if anything. But what we found is that you actually get like this interesting transfer when you allow both of these to share weights. Likewise, when you train the teacher, we thought that this would maybe degrade the student, but we found that it actually doesn't. It actually substantially improves it. So if you have a teacher that you just learn with privileged information, so it's almost like you give it the answer and it just has to solve the task itself and it just has to improve on it, it can substantially improve the student. So the teacher will move and it will kind of like trail towards the target policy, and the student kind of follows it. And by the way, I forgot to mention, but this y-axis, this is the KL between any of these policies and the base model. So if you see here, the teacher has a high KL between itself and the base model. So you can think about it's just like as the untrained Quen 4B. And then the model here, the student is like KL will equal 0, because its starting point is basically the instruct model or the base model, right? So this is why it's 0, but here this is conditional on privileged information, so the KL is not 0. And the closer you get to the target policy, the better. Okay, and just to finalize here, when we do joint training, again, something that we will observe is that not only do you expect both to improve, but they kind of like both improve jointly, and you kind of get like this kind of like best of both worlds, where as I'll talk about a little bit, like both training the teacher and training the student have failure cases, and when you train jointly, you're able to mitigate both of them. So not only do you kind of like get a little bit better reward most of the time, but you're also able to mitigate the failures of training just the teacher and just the student. Okay. So now let's dive a little bit into the results. So this is usually a small discussion that I have with when this is a little more interactive, but I'm also happy to discuss these specific things at the end, ask them to get input into what people find interesting. But just to gauge a little bit, or like prime your brain a little bit, I just presented a bunch of algorithms, a bunch of different ways that we can do the problem, which is distilling from a bigger model when we don't have chain of thought. So just think a little bit as to which one would you think would perform the best. And these are kind of like the options. And to be concrete, the most common baseline for this is SFT plus RL. And this is used widely in both like academia and in industry to kind of get models where they perform particularly bad to become proficient first, and then they're able to exploit modes via RL. And also, which ones of these do you think will perform best on other domain tasks? So there's kind of like this work right now that's being very popular, which is this self-distillation enables continual learning. And one of the things that I really advocate for is that doing things on policy, so when you sample from your own model, is substantially better at forgetting, diminishing forgetting, compared to these compared to training with a model that is with a distribution that does not come from your own model, basically. And this is kind of like the comparison that they have. So just to bring this to full picture, if we are evaluating on out-of-domain tasks, so we're not training on them, we're just evaluating on them, what we would expect to see is, if this paper holds, is that on-policy algorithms would perform the best or degrade the least, or basically just not diminish the performance the most. And we'll see if this holds. Okay, so as I mentioned before, there's this kind of like two-stage algorithm that we kind of discussed. And here, that two-stage algorithm, which is variational EM, is this purple curve here. So the main baseline that this algorithm wants to beat is SFT with chain of thought, which is this one, this yellow curve, and we see that we're able to beat it. But something we found interesting is that when we actually were running these experiments, and we first improved the teacher. So this is, if you guys remember from the previous slides, that would be this animation where we're just kind of like training the teacher. What we saw is that outperformed everything. So it turns out that you actually don't really need to do this kind of like forward training for the teacher, and then do the backwards transfer onto the student. But you can actually just get away with training the teacher, and this performs just fine. And this gives like amazing performance with a very wide gap between between this curve and the one below it, right? And this result was kind of like one of the first ones that inspired us to go into this direction, because we saw that maybe there's something really powerful here, where when you allow these models, these teachers and students to share parameters, you get this really interesting like forward transfer. Okay. Now to go into some of our main results with basically all the algorithms I presented. So these are the in distribution results. So if you remember from earlier, I said that we were evaluating on Talbench as well as Travel Planner. So these are the scores for both of them. And what we find is that not only are we able to beat our main baseline, which is SFT with chain of thoughts, so these are with the DeepSeek chain of thoughts, plus reinforcement learning, subsequent reinforcement learning. So this is usually like thought about as like the golden baseline. That's what most papers will use to obtain their best performance in like these agentic tests. Not only are we able to beat this in two benchmarks, but we're able to beat it with like every single configuration of our algorithm, basically, except this self-distillation. So this reverse scale baseline. And we're also able to substantially outperform RL. And we see that, as I mentioned earlier, if you do SFT without the chain of thought, so this is kind of a scenario where you're just trying to distill from these models, even though you don't have chain of thought, and then you do subsequent RL on top of it, this actually makes the model worse in some cases, and in the other cases, it doesn't really, doing any of these algorithms is still substantially better. So if you're missing the chain of thought, doing any of these algorithms is substantially better, no matter the setting. But which one is best will depend on a few things. And basically, we're going to dive into those caveats above now. But first, I kind of want to like highlight these other distribution results. So first of all, I'll take a step back and I'll rephrase what I said a couple minutes ago, which is that if the results from these papers, specifically the continual learning one, hold true, that paper again basically just says that if we're sampling on policy, it will most of the time, or it will be better at forgetting compared to sampling from a different distribution, from like a different teacher, right? I believe they do have caveats, but that is basically one of the main things they're showing, and they're trying to one of their main conclusions. But something that we see here is a little bit different, and the story might be a little bit more nuanced. So here, just ignore the two other plots for a second, and we're going to dive into like the results as like Quen 4b. The main thing to note here is that the SFT with chain of thought plus RL baseline, this comes from a different model. So these are traces not from our own model. We're doing SFT, and if this was true, these are tests that we did not train on, so we would expect them to degrade substantially. So the baseline that we want to like always like compare against is the base model. So we're training on a different task. So if we're training to a different task, we would expect degradation on this task that we're not training on. But what we observe is that if we do SFT and then we do RL on top of it, this performs the best. But not only that, but then also the iDistill, so the models that like either only train the teacher, only train the student, or train things jointly, degrade the least, and in some cases improve. And most interestingly, the on-policy baselines, such as self-distillation, which is fully on policy, as well as like naive RL, are the ones that actually degrade the most. So this is not to like invalidate the results of that of the other paper, but this is just to add things that the story might be a little bit more complicated and nuanced than we currently understand. And these results are not necessarily like super conclusive that like everything they're saying doesn't hold, but it is a contradiction to some of the results. And likewise in Quen 8b, we do see that now self-distillation, which is this green curve, this green bar over here, does perform the best and is able to outperform SFT plus RL. And this is a purely on policy baseline. But we do see that the biggest degradation happens when you look at the RL baseline. So the RL baseline significantly degrades compared to the base model. So these are just kind of like very interesting results that kind of highlight this this discussion of whether or not LLMs are truly training on policy with LLMs leads to less forgetting and more forward transfer. I think the story is a little bit more nuanced. And then I don't have time to go into the R1 distilled discussions, the results, but I'm happy to answer questions. But the TLDR on it is that not much happens, and nothing really degrades except SFT with RL. Okay, so now this is the part where I think it's like the most interesting to me. So the previous results basically just say, hey, we can distill from a frontier model without a chain of thoughts. This is possible. We can do this. Great. We have good results. We show that we can even beat it if we have the chain of thought. Not only can we do this in distribution tasks, but we can do that also in out of distribution tasks. And basically, for most papers, this would be already like, okay, we're done. Like this is already it. But as you may remember earlier, I mentioned that we had 3 different types of privileged information. And the most interesting part is that the results that I gave you were for the best type of privileged information beforehand. So the story changes depending on what type of privileged information you use. So I'm going to zoom into one of these. But basically, what we're looking at here are how all these algorithms perform depending on what type of privileged information we use. So this purple one is the tool calls only. So this is when we don't have the tool calls and the arguments. This yellow one is the self-generated hints. And then this blue one is the tool calls and the arguments. So just to kind of like reiterate, the tool calls are the ones that have the most information, the tool calls and the arguments. And that's because they're basically just soft Oracle answers. So they're the most information you can get, and they kind of like have the answer. So if the model just followed these steps, it will be able to achieve the task, right? So they have the most information. The self-generated hints have a mix of mostly like high-level information and like as well as like guiding on how to do things. So they're the ones that have typically they're the ones that have the second most amount of information. And then the tool calls only have the least amount of information because they more or less act as suggestions, because you don't to call these tools you need the arguments, right? If you don't know the arguments, you can't call the tools. And some of the arguments are pretty important because it can be something like the user email, right? So if you don't know the user email, you have to somehow get the user email. So you have to navigate the environment to get the user email. But you know that you need to call these certain tools at some point, right? So these have different properties, and this is kind of one of the main things I want to highlight. So the first thing that we observe is that basically as you increase the information density that you have in the privileged information, the KO between the teacher and the student at the base model goes up. So this is here the x-axis is the KO between the teacher and the student, both untrained. So just the base model, teacher, which is just the model conditional and privileged information, and the student, which is not conditional and privileged information. And as you increase the information granularity, the KO increases. And what this means is that the model is acting significantly different when it has this type of privileged information versus some other. And this leads to some really interesting results. Likewise, here, another important factor is this kind of like bar plot here, and this is the hint utility. So you can think about this as like from an untrained model perspective, so just from the base model, how much more reward are we getting on the training tasks when we condition on privileged information? So this is just the reward from the privileged teacher minus the student on the training tasks for the base model. Okay, so now let's dive a little bit deeper into the results. So now we're checking like when we only train a student. So here, what we're doing, just to reiterate, is we're taking samples from the privileged teacher, and we're using the student to learn from these traces. So something we observed is that if you have high utility privileged information and it's low KL, your model can learn from them very, very, very well. So as you can see here, you can kind of like get like very, very high reward just from this type of setup. But interestingly, as the KL gets higher, you end up in the situation where the model's performance actually degrades. And this is very common in these kind of RL settings because you're training with what's referred to as off policy data. And typically it's well known that like off policy data is harder to learn from. So it's kind of like an expected behavior, whereas the traces from the teacher become more off policy to the student, even if we train for them to stay on policy, the performance is not as good. Now, another interesting aspect is that training from the teacher is actually a very good thing to do. So training the teacher only. So this is not the students not involved. We're just training the teacher on policy. Acts very well. But something we found is that very interestingly, if the teacher KL is too low, so the teacher and the student act too similarly to each other, and you're training the teacher and the student end up collapsing onto each other. And if this happens, the teacher learns to ignore the privileged information, which heavily degrades his performance. So it's very important that when you're doing this sort of like learning from privileged information, you kind of like you make sure that you have your teacher acts substantially different from your student, or else they'll just end up collapsing into each other, and then you won't make a very good performance. And then there's like not error bars in the screen line, but basically this is within like standard error. The performance is within standard error of this, so they kind of like fall within the same performance. But interestingly, if you have a high KL between the teacher and the student, and you just train the teacher, then you get a really good transfer, and you can actually learn very, very well. So it's kind of like the reverse of what we saw before. And now finally, on the other hand, is if you do this sort of like joint training, this kind of stabilizes the process. So you do not have the issues that you mitigate the issues that you would have with training the student or just training the teacher, because you're kind of like able to get away with it by just kind of like balancing both of them. And you end up with like a very stable, high reward solution, where training both leads usually, it may not always lead to the best solution, but it's never the worst, basically, is what we observe. So as like a common recommendation, what we say is like, if there's no compute, there's no effort to like trying to get the absolute best performance, training jointly will kind of give you the best of both worlds, and you basically don't have to worry about anything, and it will just work. So we recommend training jointly in the paper. Okay, and just quickly, what I'll talk about is what matters for like this on-policy self-distillation. So they just the reverse scale baseline. So interestingly, we expected it to fall similarly to just training the student, in which as the KL got higher, it would perform worse. But we found contradictory evidence for this. What we actually found was that the information granularity is what mattered the most. So the amount of information within the privileged information, it led to better performance, basically. And we measure here like the information by the hint, the utility in the hint. So the more useful a hint is, or the privileged information is, the more information. As you can see here, typically the ones that are better acting, except like in this case, for example, tend to perform better. But we did find like one very interesting exception, which is in this case in Quen 3.8b, where usually in this case, we would expect this, if the results were consistent with the other ones, we would expect this scenario, the tools on the arguments, to perform the best. But what we found is that actually performance the worst. So this kind of does indicate that like there is more to this story than just information granularity. There's likely that you need to balance information granularity as well as a little bit of the KL, because this does have the highest KL of any setting that we explore. So we still believe that making sure they have like moderate to low KL, but very high information density is probably the best that you can do for this. Okay, and I won't get into this very much, but we ran a very comprehensive study on a suite on like this beta, so this parameter that modulates the KL in all of these objectives, the KL optimizer in all of these objectives. And what we found is that while there's no like consistent value of beta, that just performs the best in all of these. In 17 out of 21 configurations that we tested, beta bigger than 0 is beneficial, although tuning for it does like require like is required for best performance. So yeah, like no value is fixed. So no value is fixed. Sweeping for this is likely required, which is unfortunate. But if one does have the compute budget, sweeping for this will ultimately give the best performance. But this also does suggest that the KL was a fairly important component of the algorithm. Okay. And then, so some future / ongoing work. Sorry, I have a link here. So I'm currently working on using this kind of like algorithms for preference learning, as well as just a more concrete empirical study on forgetting in L1 post-training. As I mentioned, I think the story is not very conclusive, and there's other things that we can do. But yeah, I'm interested in to hear like any feedback or any additional questions from anybody in the crowd. So yeah, I just want to say thank you. Thank you, Halun, and everybody for listening to this.
Thanks a lot, Daniel. Amazing for the great talk. And I really like the animation from your blog. It's really cool.
Thanks.
And also for our audience, if you have any questions, please feel free to post any questions online, and I will moderate that. But maybe I can start from some of my questions. Actually, I think there are really lots of things to discuss here. I really think it's a really amazing talk. Maybe I will start from this one. I feel maybe one of the most striking results is that the pipe distill you proposed can outperform some standard SFT with CLT plus IO pipeline in some settings, right? So I feel this is really interesting. I can understand, for instance, about the speaker motivation. For instance, if the model is fully black box, you cannot access it. Definitely, we do not have the CLT to distill. I just wonder how to interpret better about for those model with CLT, your method is also much better than that in some settings. Is it purely because of the distribution shift stuff on that? I think maybe this is the key. So basically, my understanding is that depend on the privileged information, it is easier to close the gap of the distribution shift. Is this a correct understanding?
Yeah, so I think that's a really good point and a very good question, and I think you kind of have it bang on. The main reason why we attribute that you can do better with Distill versus SFT with top plus RL from a bigger model is because ultimately the SFT from a bigger model will be more off policy than your own traces, even if it's conditional on privileged information. So the distribution shift, as you mentioned, is a little bit larger. So even just like this kind of like learning from this privileged information that is very easy for you to learn from because it's coming from yourself and it's very on policy, this is typically just better.
Yeah, gotta understand. And also, I think maybe there's also a reason is because I feel sometimes the chain of thought has a lot of noisy, right? Like if you ask the model for the same question, your output is facility actually is quite noisy. So it's very hard to distill. But actually the action probably is more reliable.
Yeah, the action is very reliable. Yeah. And the chain of thought often comes with a lot of like syntactic noise. So there's like different like synonyms for words or different sentence structures that basically between models that basically mean the same thing. But if you look at them in model space, they're very distinct because the model users are very confident in what they're saying a lot of times. There's a few studies showing that there's very few uncertain tokens. Like there's very few tokens with very high entropy where the model is like has a lot of like branching forks, but everything else is very sure about. And if you take into account like synonyms, for example, these would be very IKL and would likely throw up the optimization process, and they're very common, right? So it's kind of a good way to think about it.
Got it. And maybe another question is about the PI utility and the KL divergence, I guess. If my understanding is correct, so you said like the ideal case is we have the low KL and the high PI utility, right?
Yeah. So ideal case, yeah, there's a bit, it's a bit complicated, but the ideal case is basically you just have like low KL and high utility in your published information. And if you're able to get this, then you're pretty golden.
I should understand this because I'm not sure if I misunderstood something. So my intuition is that, for instance, if a PI is really informative, whether it will naturally lead a very high KL divergence, or this is not exactly true.
Yeah, so
like
so you can so surprisingly we found that like you can have very informative, so you can have PI that shapes the distribution to much higher reward without changing the KL that much. So that would be kind of like this. But ultimately we have a different plot in the paper that shows that like once you actually train on the PI, it's also important. And then this story looks a little bit different. So then this is like significantly higher than this, for example. So there's like different axes of utility that you can think about it. But ultimately, if you can get like some sort of PI that gives you like good delta on your reward on the training tests, at a low KL, this should work well. Like that should just be, you should be fine.
Reasonable. And also, maybe one naive question is, I feel all the setting is about the teacher and student share the same parameter. So this is by design, right? So basically you consider the setting. So I guess maybe, so I guess that will have some effect on the difficulty of the KL divergence between the student parameters and the teacher parameter, right?
Yeah.
Like, I mean, if you change to let's say if the teacher and student are different architecture, I assume maybe it still holds, but will there be more challenges?
It may. I mean, at that point, like if there are different models, then you have to deal with like both like the syntactic and then the semantic differences. I think here usually you're mostly working with semantic differences. So you're mostly working with differences between like how the models reason about things and how the models want to act. Whereas if you have different models, you have to close the gap between like the syntax of ways that things models verbalize things, right? So I do think there is like a little bit of a difference. We didn't test with other models, and there's like on policy distillation by Rishabh Agarwal and that Thinking Machines posted. those works are with different models, and those seem to work pretty well. So it's possible. Yeah.
Makes sense. I also just wonder, I'm not sure if I missed something. So I feel all the actions you talk about is kind of like on some structured tasks, right? If I can call it like that. So for instance, it's very structured tool use environments, so I can very easily understand which tool I'm using. So this is exactly action. So I just wonder, have you considered any unstructured tasks? For instance, like some open-ended text generation, like it's a little bit hard to design what the exactly action is.
Yeah.
So for instance, yeah, I mean, like write an open-ended paragraph or something like that.
Yeah. Maybe. So there are ways to go about this. There are some works that actually study this setting where they're trying to target so there's a paper called Quiet Star, if you're familiar with it or people are familiar with it.
Yeah.
That kind of have this way that like you're trying to do like on policy generation, but your reward is like basically the observed data. So the log probabilities of the data. That actually has some interesting relations to what we did. And you can kind of do it that way, where basically you're trying to generate on policy, you're trying to generate data that looks very similar to the summary or to the text that you like we're targeting, right? So yeah, there's some interesting things that you can do on this axiom. I am exploring and maybe this is something we can talk about offline, but like I'm exploring with some collaborators how to use these kinds of things for preference learning. So this kind of for these non-verifiable tasks, and I think there's something that you can do where you basically the main thing is that in those settings you lack a reward, right? But you might have a model where you're able to steer and act as like a pseudo reward model, where its log probabilities kind of act as like a reward model. So I think there's ways to go about this to basically like leverage a lot of this stuff.
Definitely. I think that case it will be really make this work more broadened to more applications and scenarios, I think.
Yeah.
Actually, I'm good about everything. So for more questions, we can discuss offline. And let me double check if we have any audience online posting any questions. Okay, I guess now I didn't see anything, but we're also right on time. So thanks again, Nero, for the great talk. So maybe our team will reach out to you if we need to summarize your talk and to ask you for some proofreading.
Yeah, of course.
But we really look forward to discussing more offline, and really happy to have you here.
All right. Thanks, Arun. Okay.
Thanks,
everybody.
Thanks.
Bye-bye.
See you. Bye-bye.